Okay, here's the case 3 example from class 1 of ES211. We're dealing with the acceleration of a slider. We happen to know that it acts with this kind of relation, -2 square root of 1 minus v squared. So acceleration is a function of velocity. Acceleration and velocity are in terms of feet per second squared and feet per second. And the system starts from rest when x is equal to 1.5 feet. And that's when time starts at 0. We want to determine the position of A when the velocity is -0.6 feet per second. And we want to find the position when the time is equal to 0.3 seconds. So I'm going to switch over and use my document camera here, if it will let me into this show. Okay, so here we go. This is case 3 example. And so we're given that the acceleration is -2 square root of 1 minus, and I almost drew that like a mu. It looks like a mu in there. It should be a v, so v squared. There you go. And we also know that at t equals 0, x is equal to 1.5 feet, and v is equal to 0. And so for the find, we want to find x when v is equal to -0.6 feet per second, and b, we want to find x when t is equal to 0.3 seconds. So because this is a function of velocity right here, we want to use case 3, right? So case 3 is A is equal to v dv dx. Oh, by the way, in case 3, I should say. Okay, so in part A, we're going to use case 3. That is the case when this is a function of velocity, but because we're looking for position, we're going to go ahead and use this. That's the reason why we're using this right here, because we're dealing with acceleration as a function of velocity, but we're focused in on position. So in writing this right here, we can draw out that x over to the side and take acceleration and bring him over to the other side right here. All right, and then integrate right that. And so we can integrate that because everything over here is a function of velocity. We can integrate against velocity. That's the concept that we're adding into there. So I can say the integral of x, and we're going to take the integral from 0 to v, right? And so, by the way, this is going to be from 1.5 to x, right? Because it's corresponding with each other. Here's 1.5 and here's 0 right there, right? They correspond to each other down there, and then we're leaving these as variables. So we take the velocity and divide it by -2 square root of 1 minus velocity squared, dv. Now, that's an interesting integral. We don't necessarily know how to do that off the top of our heads. We could start to manipulate with it algebraically to try to sort things around and get it into a form we're familiar with. We could go to Wolfram Alpha, but we could also go to useful links and resources and go to our integration tables, which brings up a nice website right here for integration tables. Very handy. I'll zoom in here a little bit, and if we start looking at the forms, we could see that this guy right here is close to what we're looking for right there, right? Because we have the velocity up by itself on the top. We're dividing by the square root of a constant right there, and that constant might as well be squared. It's totally okay with us. And then minus, and then we have that velocity squared. So if we look back at that, that's kind of the form that we have, right? The variable up here, something like this doesn't matter right there. It's just a constant, so we can move them over. And I need to double check and see my thing right here is asking me if I'm still there. Or no, wait, we might have somebody here. Do we have somebody here joining us? Oh, we do. Okay, so we'll pause this. Okay, so we're back. Let's see, we come back over to, where were we? Integration table. Yes. So that's the form of the thing. So when we go to write that down from that form, what we're going to find, okay, so for over on the left-hand side, we're going to have x minus 1.5, right, from that integration. And then here, from that integration table, we're going to, we pull that -2 out, and we also are going to get a negative from this form, right? The form told us, I'll write it over to the side, negative a squared minus x squared was the answer to this. So that negative right there gets rid of this negative, and so what we're left with is 1/2 square root of 1 minus v squared, and we need to take that from 0 to v. Right there, I didn't do the thing in. But now if I plug those back in here, I get my x minus 1.5, 1/2, and then inside this thing, 1 minus v squared minus square root of 1, duh. And so I can write this out as equaling 1/2 v1 minus v squared plus 1, right there, right here. So here is, I boxed it. Maybe I shouldn't box it. It's not an answer, right? So that's actually a pet peeve of mine when people do that. So I need to not be a hypocrite and not box things that are non-answers. Some people go a little box crazy and they just start boxing all kinds of things, but really we just only want the answer boxed. So anyway, so for part A right in here, all we have to do is stick in negative 0.6, which didn't even matter that it was negative because it's going to be squared right in here. So at v is equal to negative 0.6 feet per second, x is equal to 1/2 square root of 1 minus negative 0.6 squared plus 1. That ends up being 1.400 feet, and that's going to be the answer to part A. And then for part B, now we want to find the position when at a time, at a particular time. So we have to do the whole separate integral right here, right? So we know this relationship is right here, but now we want to solve for time. So we say that the acceleration is equal to dv dt, and rewrite the thing out as dt is equal to dv over a, or I like to say 1 over there. So if we do that right here, we take dt is equal to, I'll write it over to the side. I'll say 1 over negative 2 square root of 1 minus v squared, right? dv, let's integrate that. And we do know from our limits that up above right here, right, that when v is equal to 0, time is equal to 0. So we can have that there and there, right? And then once again, this is going to be another integral form that might not be obvious to us, right? So we're going to have to look up the integration tables again. And going to the integration tables, I think I've seen this one. It's sort of a weird one, an unexpected one to get. I think it's up near the top over here on the right-hand side. No. Where are you? Trying to find here. Right, so we have there you go, right here. Yeah, that's an interesting one right here. That you get the inverse. It equals the inverse sine of x over a. That's an interesting one to me. I would not have that to jump out at me. So anyway, what we end up finding from this after doing this integration here is that time is going to be equal to negative 1/2 inverse sine v. Right, and then that's even with putting even the limits on there of zeros in there. Okay, plugging that into the thing. So if you take the sine of both sides of this, what we end up finding, right, and we multiply that over to the side and whatever, is that we're going to have the v is going to be equal to the sine of negative 2t. That's a really weird thing to happen out. So when we want to try to solve for this right here, we could put in the 0.3 seconds, right? So put in 0.3 seconds, and so at t is equal to 0.3 seconds, we get the velocity is negative 0.5646 feet per second. Interesting, huh? An interesting outcome. And so then we will now if you, let's see, is that what we're asking? No, we want to find the position. That's the velocity. So if we plug that back in we're going to plug that back into here, right there, right? We could plug that velocity back in and then find the position, because that's what we're being asked, is for position right there. That's interesting. So I say that that's going to be x is equal to 1/2 square root, you can't see me writing, 1/2 square root 1 minus negative 0.5646, which is really close actually to that negative 0.6 that we had before, which is weird. I don't know why we would have done that, the creators of this. So we end up 1.413 feet. Okay, so the answers to part A is going to be x is equal to 1.4 feet, and B, x is equal to 1.41 feet. That's not very exciting, is it? I didn't create this problem. But that's the solution for these.